Hello everyone. In this video, I want to talk about quadratic sequences. So a quadratic sequence is a sequence of which its nth term can be written in the form of an squared plus bn plus c, where a, b, c are constants. If you've ever studied functions, you might have come across quadratic functions, and they do look very similar, or in this case, it's n instead of x. How might you spot a quadratic sequence? Well, if I were to give you one right here, let's say 3, 6, 13, 24, and 39. You'd probably be able to tell me immediately that this is not linear, right? It is not going up by linear fashion. But how is this quadratic? Well, in order to verify this, the second difference of the sequence has to be constant. So if we take the first difference, this is 3, this is 7, this is 11, and this is 15. So the first difference is changing, and in fact the first difference is linear. However, if we see the second difference is now 4. So as you can see, since the second difference of the sequence is a constant, that means the sequence is a quadratic. Because we know that every quadratic sequence can be expressed in the form of an squared plus bn plus c, we can use this fact to help us to solve for the nth term of any quadratic sequence. So I'm going to start off with a table. Let's just draw this real quick, where we have n on the top, that is the term of the sequence, and we need the first 3 terms in this case. And I'm going to write on the side the sequence itself, the first difference, and the second difference. We can actually just plug these in, right? So when n equals 1, this is now a equals plus c. And for the second term, that's going to be 2 squared, which is 4. So it's 4a plus 2b plus c. And the third one is 9a plus 3b plus c. And to find the first difference, what we need to do is subtract these two, just like how you would do a normal sequence, where instead of these a, b's, and c's, you just have 2 numbers, right? To find the difference of them, you need to subtract them. So likewise, we're going to do the same. This is going to be 3a plus b, and this is going to be 5a plus b, and therefore the second difference is just 2a. And so if we have a sequence previously, that is 3, 6, 13, 24, 39. If we want to find the nth term of the sequence, then actually we only need the first 3 of these terms, because this is where n equals 1, 2, 3. So this is going to work for any of these sequences. If I just redid the differences, we can see this is 3, this is 7, and therefore the second difference is 4. We can just start equating this from the table. So since the second difference is 2a, that means 2a equals 4, and so a equals 2. So ready, we know it's going to be 2n squared. Then 3a plus b is now 3a plus b is 3, yes. Therefore, since we already know a, which is 2, so therefore this is 6 plus b equals 3. We now know b is minus 3. And we work our way backwards until we reach the top line. That is a plus b plus c, yes, is 3. And we know that a is 2. We know that b is minus 3. Plus c is 3, right? And so we can work out all 3 of these integers this way. So minus 1 plus c is 3. And therefore c is 4. So now we can conclude that the nth term is 2n squared minus 3n plus 4. And in fact, you don't really have to draw out this table every time you want to do a quadratic sequence. You could just remember that the second difference is always 2a, and just remember it this way. But I think knowing the table helps you understand why that's the case. But I'm not going to stop you if you just do the simple way, which is just remember, right? You work out the second difference, you divide that by 2, and you always know that that's going to be a. And so just by memorizing these three parts of this table, you can work out any quadratic sequence. But if you were, I don't know why you would, but if you were to take the second term at the end, like 4a plus 2b plus c equals 6, that would still work. And likewise, 9a plus 3b plus c equals 13. You can use any of these as long as you find a, b, c in the end. You can work out the nth term of the sequence.